We can start, and then I'll go ahead and share my screen. But before I get started, I just wanted to thank you, Nick, and Laura Turner from our Caterpillar Technical Information Center, really for inviting us to present to the Peoria Riverfront Museum's program here for Engineering Week. I manage our corrosion engineering and our advanced materials technologies corrosion engineering program, and we reside within the integrated components and solution organization, and I can tell you we really enjoy the opportunity to promote, celebrate, and educate in events such as this. So thank you very much. So I will go ahead and tell me if I can share my screen. Somehow I lost something. Can you see me?
Yeah, I see you.
All
and
right.
yeah, so at the bottom there should be the share screen.
I got it here. So can you see my screen yet?
Yes.
All
so
right.
if you want to turn your video off, you're welcome to. We got your screen.
And that's not stop video again here, right?
Down to the left, yeah, stop video.
All right.
There we go.
Oh, great. All right, so I'm going to get started. And again, there's one other person I want to recognize here, and she's done an awesome job, and that is Anka Marcoux. So Anka and I work together, as I mentioned, in the Advanced Materials Technology, Corrosion Engineering, and Plating Group. So today's topic is corrosion and methods of protection. And the objective here today, along with the topics, is really to have a good understanding of the cost of corrosion. You'll have a better understanding of the definition of corrosion and the various types. I'll get in a little of the oxidation and reduction reaction, which is, but I won't get too technical in that area. We'll talk about some methods and of protection. And I want to explain from the standpoint of, the different types of careers and roles of people. Really, it's just about 3 or 4 here roles that we actually work with. And then I'm going to end it with really an opportunity, a money-saving corrosion prevention tip for people that are homeowners. United States, there's constantly people are trying to determine within this, the government and through the National Association of Corrosion Engineers, they put a figure to, what is the cost of society for corrosion, and it's roughly $276 billion, and it's probably more, but that was the latest figure that I've seen. And you can see kind of the breakdown, the transport in this pie chart here. The transportation utilities is close to 35%, followed by manufacturing, little almost 32%, and then construction at 18%. And then the government and purchases, 7.3%. And then you can see some of the other services and local government. I will tell you that everybody sees corrosion. They probably don't see it as, I think after this slides that I'm going to show you, you're probably going to look at things a little differently. At least I hope you do. So I'm going to share with you a number of different pictures that I've taken about 10 years ago, actually, when I gave a talk at a convention in FabTech. And so, like I said, about 10 years ago, I went around on Saturday afternoon before my event, and I said, I'm just going to take some pictures of some areas, and this was a business park, and people probably can recognize where it's at in the Peoria area. But at this point in time, they really didn't have too many residents inside that business park, and so very quickly, going in this area here, you can see that there was corrosion throughout the facility. You can see the bleeding rust on the concrete in the upper left. And then on the light post, you can see it, the bleeding and the rust coming down, as long as with the corrosion, and some of the cracks and crevices where they kind of capture moisture. And then really on edges and welds, you can see it. The same was hold true as I went to one of the hospitals. I knew that they had, in the last couple of years prior to taking these pictures, that they'd put these new light posts in, and from afar it looks great. And sure enough, when I go down to the area where maybe there's an access panel or with edges and welds, you see where obviously there's some corrosion. From there, I went to take a look at home improvement store, and really on the outside you can see that they store some parts out there, and sure enough, these things probably haven't been out there more than 6 months, but there again you can see the edges and welds. There was corrosion already forming. So the point I'm trying to make here is that a lot of things that you buy, and if you're storing it outside, due to the way that it's actually designed, you might realize now that where you might have an issue and what you might want to do to prevent it. So there's another concept that I want to bring in here is when we manufacture things, there are some manufacturing types of equipment that we use, like laser cutting, that'll leave an oxide film on. So the paint will actually stick to the oxide, but the oxide over a period of time will stick to the metal. And so you'll start seeing some areas where the paint or coating that's put on there could pop off. As well as I'm showing the same type of thing, poor edge coverage. It's very difficult to put a coating actually on the edges. So that's where you're going to see corrosion first. This other item here, that this rack that goes in the back of my hitch, this was the third one that I actually bought. I got a little smarter after a while, but this expanded metal there, obviously a lot of surface area there, edges and stuff that, it doesn't take long for it to start showing corrosion. And the last thing you want to do from a safety standpoint is when it starts to deteriorate. And because it's not that expensive, it was easier to actually buy a new one than really try to fix it up. But these are some of the things that I came across. This was probably the hardest purchase I had. You can see on the left, bought a number of bikes for the family, for the kids, my wife and myself, and we wanted a way to at least take 4 bikes, although we have 6 of us all together, but wanted to at least be able to put 4 bikes on there. So my wife wanted me to purchase this this rack, and it was, I think, $249 or somewhere around there. And I just was kind of quiet, and she's like, "What's wrong?" And I'm like, "Boy, I can just look at this whole thing that I'm going to pay $249 for, and it's not going to take long for it to kind of show some signs of corrosion, rust." I didn't mind something like this because this was easy to probably spray paint, but the same thing. And so, as I mentioned, you start seeing these pictures and you start looking at corrosion. It's not surprising. Some people came to me after I gave a talk at Fab Tech, and it goes, "John, I can't get it out of my head. Everything I look at how it's designed and where I'm going to see corrosion because there's moisture involved in oxygen," and I'm going to talk about that. So, we talk about what is corrosion. Corrosion is that deterioration of a material, usually a metal or its properties, because of a reaction with its environment. And here I'm showing a picture of components in the manufacturing environment, different types of components that you can see here that are showing some corrosion. So what are the 3 things, or the 3 main things that we need to really have corrosion, and talk about in liquid form here? That's what I'm referring to. Is it really involves, metal, water, and oxygen. So over on the left, that's what we're kind of showing in that image. And I'm first going to introduce here the oxidation type of reduction reaction that occurs on the metal. So you can see in the gray area there, we're looking at a metal, and the oxidation is really the oxidation is the loss of electrons. And so as you start seeing electron flow, and reduction is the gain of electrons. So as the electrons flow, and you see the oxidation, that's where you're going to see the actual pitting in that case here for the corrosion. But obviously, although most of the things that I'm going to talk about are going to deal with ferrous materials, there's metals naturally exist as minerals, and then they're refined, and you can see that there's different oxides and oxyhydroxides that accompany composition, and then the mineral here, but it's refined into aluminum, copper, and iron. So as you understand, as we refine these metals, they're really unstable. And so the top right, when we look at the metal out there, they're going to have this tendency to go back to its native form, back to this, the form of the mineral, you know, which we essentially refined. So, and it does that because of the environment that it's in. I'm going to introduce another type of, I'm going to introduce something else here that that's really starts to form, and this is when metals are spontaneously formed. You know, there's this oxide layer that that's you can't see, and you can't see it, but with your eyes, but you're seeing the oxygen molecules there forming on the piece of the metal. And depending on the type of metal, it could be more of a cohesion where between the oxygens, you know, there's a lot of strength or an adherence, or to the actual substrate itself where that oxygen is, and that's adhesion. So this type of oxygen that forms initially generally is a semi-protective type of oxygen, and then as it's as you'll see here in the future slides, as you start seeing more oxygen and more moisture, you'll start seeing, especially with an iron type of situation, or iron metal, you're going to see the formation of rust. So it's important to understand really electron flow, and we're just going to touch the, you know, just going to touch a couple points here, but lithium, you know, so if you take a look at some of these lithium, potassium, barium, calcium, the different atoms here, they'll want to actually oxidize fairly easily. So the ones at the chart here at 4.5 on the left-hand side, they will give up that electron very, very easily. And down below, you're going to have gold, platinum, silver, and copper. Those atoms typically don't like to give up those electrons as easily, and so that's the reason why you don't see the oxidation that frequently. Over on the right-hand side, we're really talking about not only the you know, the types of metals, but actually the alloys. And the point I want to make here again, this is relative to other components. And I do want to point out that at this point here, that when two different metals come in contact with each other, depending on the potential difference and how far they are apart, for example, on this right-hand side, there's a potential difference, and two metals will actually create this galvanic reaction and accelerated corrosion. So when you design things, you typically want to try to put the two different types of metals or the alloys fairly close together so that potential is actually minimized. So I mentioned, you know, gold and silver and copper, and really from the standpoint of platinum, gold, and silver, those are commonly used in jewelry because they don't readily oxidize, and they're the most noble. So they come in a pure state, and you can see on the periodic chart there's others, but these are really the common ones. And like I said, there's a reason why they use this for jewelry. So over on the left-hand side, like I said previously, you know, we're really focused so far on really rust occurring with ferrous types of substrates. Now I want to talk about a little more on copper and aluminum. And obviously you can see the Statue of Liberty. And, you know, corrosion is kind of, or oxidation and corrosion is really in the beauties behind, you know, on the beholder here. Sometimes people like the different types of oxidation that occurs, for example, on certain things like copper. So you get this blue-green oxide, this patina appearance. And in many cases, people like that color. Obviously, when you talk about iron and rust, you know, very few people like that. And then over on the right-hand side, you know, when I grew up, there were a lot of things that were aluminum that weren't painted because it's difficult to actually paint aluminum without a good surface pretreatment. But originally, when you would get an item such as a ladder or a screen door, it would be really shiny. But then aluminum oxide types of forms, and it starts to get kind of a grayish color. And that oxide, in both cases here with copper and aluminum, it's really a form of protection So it oxidizes and it protects for further type of degradation. Because everybody's at a different point probably that's listening to this presentation, I have a few slides here that are a little more technical, and this is one of them. But I'll try to do my best in explaining this here. The line, so if you look at the image in the middle near the top, I'm showing here that oxidation occurs at the anode. So what you want to remember here is oxidation at the anode, not a type of this type of reaction here. And again, what we're showing is that iron wants to give up those electrons, and it's going to give up those electrons and go to the cathodic area or the cathode area, and then the ions from the iron is going to go into the solution, and then it just really promotes the whole corrosion types of process because it's going to form with the water. And generally, the rust is actually going to form kind of in a different area, maybe not in the same area as the cathode. But if you look down below, the oxidation reaction or the loss of electrons is, iron. Here we're showing an example of iron, +3 state and the 3 electrons, and the same thing with the oxygen, +4 electrons. And so when you put that together, you have iron plus, 3 molecules of oxygen and Fe2O3. So again, the big thing that you just want to remember that the redox reaction is really involves the transfer of electrons. And earlier I mentioned, you have this semi-protective type of oxide that forms, and that can last a really short time or it can last a little longer depending on the environment that it's in. But as you increase the amount of oxygen, you start to form the non-protective on the ferrous types of material, and this is how rust forms in the Fe2O3 in the ferric state. So higher oxygen conditions really is one way to actually accelerate, the corrosion for ferrous types of material and how rust forms. Now I'm going to talk about some of the physical and chemical threats to that oxide skin. Like I mentioned, it's kind of there for initially is that protective type of measures, but there's other things that could actually start to accelerate some of the corrosion on a nice metal surface, and that's if you do anything physically on that surface. So there up at the top on the physical image here, we're showing that we're drilling into that block of metal, and as a result, we're going to make that surface very active because we're doing something to that surface. So physically, you can do certain things to the metal to create faster oxidation in the reaction. And then chemically, because in the manufacturing environment, if you look at that physical picture here in the middle on the left-hand side, you see that we're using what we call a metalworking fluid or a coolant. And that is used to actually take the heat away from the tooling as one aspect, and the same thing with the parts, so you don't have some, your tooling doesn't burn up. But you got to make sure that now that you're introducing moisture or water, that water actually has rust preventatives in there, and it's actually good quality water so that you don't accelerate the corrosion during the manufacturing process, right? Because what we've learned was the fact that oxygen and moisture and the metals, you're going to have corrosion. So we put different types of, or we purchase different chemicals for that, and we want to make sure we manage them. Now over on the right-hand side here, when we talk about the chemical pH, so let me introduce pH. pH is, it runs from 0 to 14, and the 7 being neutral. Below 7, we're in acidic conditions, and acidic conditions typically are going to accelerate corrosion on metals. And then above 7 is alkaline, sometimes referred as basic. And generally when you get up to maybe 11 pH and maybe 11 to 13.5, 14, you're going to see that things you can do with pH to kind of slow down the reaction when you have exposure of a fluid with a metal. It's probably not the best image on the right-hand side, but it'll make more sense here as I go through here. But really we're trying to show is that conductivity in the water. And this is what's used a little later in the slides, where higher conductivity water, you can see the light bulb go on because of the flow of electrons and it being electrolyte. So that's really TDS, total dissolved solids, or conductivity. And then over kind of on the left-hand side, we're seeing that those are ions. So along the thought of, I'm telling you these process chemicals, I mentioned that we've got to make sure that there's good water quality to start with before we actually add these chemicals to, of course, they're colored in this picture here, these chemicals that for the machining fluids, and make sure that we don't have corrosion. So anybody that's in the manufacturing world will have, it'll get pretty costly, and they'll have a number of issues with corrosion if they don't really have a good fluid maintenance and control program. And that's not only on the metal working side of things, is that after you machine it, the metal, you want to make sure that you clean it. And you want to make sure that you clean away some of the metal fines and stuff that's on that component, because as a result, with that surface area, that could actually promote early on corrosion. Now, eventually, when you do that, you can take a look at this image down below, and you'll see kind of a yellow film that's in a bag. As we mentioned, you want to make sure that that part is dry and is packaged, because as we know, moisture really provides that environment for corrosion on that metal surface. And so probably what's not known to many people here is that it's really important to make sure that you package these parts. And a lot of times if you buy a part at an automotive store, you'll see it wrapped in paper, or you'll see it come into a kind of a colored film. And that colored film is actually been treated, or it's as an impregnated in their amines in most cases. And those amines, when you wrap the part or you close the container, the amines that are actually in that film or actually on the paper, they'll actually microscopically, you won't be able to see it, they'll actually form roughly over maybe a 24-hour period of time on that part, protecting it from corrosion. So if you have any condensation that builds up there, you can handle some of that condensation, not a whole lot, but that's what it's used for. So if you see any type of colored film, you can bet that it's more than likely going to have some impregnated amines in there to provide corrosion protection. And then over on the right, Northern Technologies is showing here. They're, in this case here, it's probably an emitter. It could be a desiccant, but it's providing additional VCI, volatile corrosion inhibitors, to that packaging. So we talked a little bit about corrosion. Now I want to kind of expand on some of the water quality aspect of it. We touched upon that a little bit. Again, reinforcing kind of pH, from 0 to 14. There's some items here that you can see that that when you come in contact with on a daily basis, some of the products, some of the things that you consume, you can see whether the pH is. And so here again, we're looking at Coca-Cola, and the types of colas that you have, it's going to have pH somewhere around the 3 or 4. Water, I will tell you, that's a really interesting subject. If you buy water that has been has gone through a reverse osmosis, it's going to be probably a little more acidic. And if you buy water that actually says spring water, you're going to see more calcium, magnesium, and it's going to be a higher pH. And that makes a difference probably from a health standpoint, depending on your age. People, as they tend to get older, do better with higher pH water. And then down below, we're talking about easy off. There's something, an oven cleaner that's extremely alkaline. And that removes, obviously, the different types of soils and stuff that's baked on there. The other thing that I want to, there's two other components here that I want to talk about. The next one is going to be hardness. And when you hear the word hardness, that's really calcium and the magnesium that's in your water. And so most people here in the Peoria area, since we have fairly hard water, will have a water softener. And if your water softener isn't working, or if you don't have one, the easiest way to see that you have some issues is probably in your dishwasher, or you'll start seeing some spotting. So some of the products that they have, they'll actually tie that up with chelating, what they call chelating agents. But the bottom line is hardness hardness causes some issue when it comes to corrosion. And it also leads to really the increase in the dissolved solids. And as I mentioned before, just slightly, that the higher the conductivity or the more dissolved solids you have is going to really increase the conductivity, and the conductivity of the water is going to make it more corrosive. So those are the 3 points. Up on top here, you see deionized water. It's a process to take rid of cations and ions, as well as reverse osmosis. Some people have reverse osmosis systems in their homes. And what we're showing here on this chart is that the particular water that was sampled, that was tap water, has all these ions, as I mentioned before, that you'll see in water. In DI and RO waters it's removed many of those. A lot of times we'll use reverse osmosis water for manufacturing, and then maybe we'll polish it and send it through the ionized tanks to get better quality water that they use in the medical industry. But when you, in comparison, and many times, you'll see that the tap water is going to be more corrosive. And the reason being is it'll have ions in there that are corrosive, like chlorides or sulfides. And so really what we're just trying to show here, that if you put a drop of that water on these metal plates, that you're going to see some consistency where corrosion, where they have tap water that has chloride ions and higher conductivity water. Not going to spend a whole lot of time here, but I do want to mention that how reverse osmosis, water purification can work, especially in the manufacturing environment or in the home environment. And really what you're doing is really you're taking high pressure and you're pumping it through these membranes, and they're semi-permeable, so you're going to collect those dissolved solids inside that membrane, and you're going to push through water that's actually more purified. Reverse osmosis doesn't take out everything, but it's going to give you pretty low conductivity water, roughly 50 micromole or less. All right, so fluid management. Again, touching upon the point that I mentioned a little earlier with those images, you know, the key properties of these aqueous fluids, you know, are pH, total dissolved solids, and, you know, the anions, where I was talking about chlorides and sulfides. Excuse me. I'm not going to spend so much time on the chart on the left. I just want to reinforce again that the acidic environment is less than 7. You know, and the alkaline or basic is above 7. And now referring to that chart, as I kind of mentioned before, when you start to see a higher pH, if you look in that blue area there, you'll see that there's less tendency, based on how the chart is, what the chart is showing here, is there's less corrosion that kind of occurs in that area. But there's a lot of things showing on there where it's talking about oxygen and some of the different types of passivation that occurs. But really the point I'm trying to make here again is when you have this higher pH, you're more likely to have less tendency for that water to provide corrosion. So adding on to the point that I made before with increasing conductivity and you know, that you have electricity here and you have an electrolyte. This is commonly used in, or was when I was going to school in high school. We did a demonstration with different types of dissolved solids in the moisture, and depending on how much was there, you would see the light bulb as you're putting a power source through there. You would see how much was actually conductive and how bright the light was. And obviously, as you increase the conductivity, you get a brighter light. And underneath there, it's showing a relative comparison. And I'm saying relative comparison because all water is going to show is that corrosion, as I mentioned, you know, exposing to a ferrous type of substrate. But you can see that there's a lot more corrosion when you see the light bulb being, you know, pretty bright because of the total dissolved solids. So again, total dissolved solids, the higher that amount, you're going to have more corrosion. Because corrosion is pretty complicated parts, I'm just touching the surface, and I just wanted to let people know that I didn't really focus on it because this is a pretty large topic to talk about. I'm not really talking about non-condensation, due to kind of a gaseous environment. Some of the things that people see maybe in heat treat or in some other areas, in some of the areas of utilities and stuff. We're really focusing on liquid or condensation, but I haven't yet really talked about, other than galvanic type of corrosion, which is dissimilar metals. I really didn't talk about uniform, or what we consider uniform or localized in some of the chemical mechanical interactions. So I think the best way to do that is on the slide that I have next, and it kind of shows an image, and it's helpful. This was through ASM. We teach a class on corrosion. So if you look at the first one here up on the top left, you'll see that there's no corrosion, and then uniform corrosion is coming across that whole part. But what's common is that when moisture sits on an area, and maybe it has corrosive ions, a lot of chlorides there, whatever, you're going to see pitting. So the corrosion is going to go straight down. In the early pictures that I was showing, due to design, you can have crevices or areas that's kind of collect moisture. And so that type of corrosion is, we call is due to crevice corrosion. I mentioned earlier, and I'm going to continue this point here, galvanic corrosion. So electron flows, depending on if there's two dissimilar metals, it can accelerate because of the potential differences between those two metals. I didn't really talk about erosion, so now I'm on the second line here. And this is if you're pumping fluids, you might have some actually solids in there, like fracking industry, very corrosive type environment. But as you can imagine, if you're pumping sand or you're pumping other materials, that it can provide erosion corrosion because you're wiping away from that surface. And as I mentioned, when you do something to that surface physically, you make it more reactive. So, you have a lot of things going on there from the standpoint of making it an easy target for it to actually promote corrosion. Fretting, that's a cyclical movement on a load. And then people that we work with that are material scientists, they get involved in looking at the metal and below the metal. And so they'll look at the kind of how the grains are actually impacted. And so, is it granular, intergranular type of corrosion? And so I'll show a slide here for what a material scientist kind of work on, but they'll use technologies like scanning electron microscope and then and really try to look at failure. Usually when it gets to this point and when they get involved, it's usually type of corrosion that's really detrimental. So things that fail like bridges or certain types of components on equipment or machines that like automobiles and stuff. So that's when corrosion gets really bad, or you have certain types of fatigue. So I'm not going to cover that a whole lot, but I wanted to mention that you can see the complexity when we talk about different types of corrosion. And then I'll probably show something here that is a combination of, because a lot of times there's a number of things that are occurring. I think I have one slide here when I talk about what we do in our organization, but I think I'm showing a combination of high chlorides and microbiological influence corrosion. So keep hitting the point here that what influences kind of the rust formation is really the alloy content. I just kind of briefed over the the microstructures, some of the material scientists look at in the residual stress. And I talked a little bit about surface cleanliness being important because you don't want to leave chlorides or certain types of ions that are corrosive on its surface. But in most cases, when it talks about the consumer, people like ourselves, we buy certain things that it's really the environment. So the relative concentrations of air and water, if it's acid rain, if that was a big issue, and still it's talked about, but it's picking up sulfur and chlorides, that it comes in contact with. Maybe you're close to the ocean, so the condensation that forms if you have something near the ocean, you're gonna have higher chlorides in that moisture in the air, and that's going to promote faster corrosion. pH, and so these are things that we just talked about: pH, temperature, sulfur-reducing bacteria. What I didn't talk about is stagnant water. And so a lot of times high velocity water can give you a problem, and stagnant water. So water kind of moving is really helpful. So when you have a pond and stuff, it's, you know, if you turn everything off, you're creating that stagnant type of water, and you're making it a little more corrosive. And maybe you have to do that, but that's the point I'm trying to make. Stagnant water, you'll have more types of potential corrosion. And then galvanic effects, again, it's the dissimilar metals coming in contact, and then with the environment, produces faster corrosion rates. All right, so how do we prevent corrosion? Most people, probably the most common is painting. So we paint things to make them look aesthetically nice, and on different types of components. And it could be if you're building a deck, or if you're using certain types of materials, you want to use things that are zinc electroplated or galvanized. People put in sheds, they'll put galvanized that has a lot of zinc on it. And I'll talk a little bit about some of these here, but by putting a plating on there, you're essentially putting zinc on there, and then zinc is going to oxidize. It's going to form kind of a white precipitate, but it's not going to be as ugly as the formation of rust or the bleeding of that orange color that you'd see. And then down below, you'll see this on, years ago, you'd see this on a lot of cars. Car bumpers were chrome plated, but cylinders are plated. And a lot of times when we chrome plate things, as well as other plating, it's not only for corrosion protection, but we may want lubricity, or there's other types of things that we're trying to get out of that component. So it's not just corrosion. We do things for plating and painting and a number of different things for other reasons as well. But those operations will actually slow down the rate of the oxidation. And then finally, there's a number of different types of corrosion preventatives, and I'll talk about it. These are solvent-based, water displacing type of materials. And you spray WD-40 on it, and it's going to prevent the moisture from getting into that area, as well as putting greases on. So things that you do in your lubrication, as well as rust preventative. So I want to introduce electroplating, and it's an oxidation reduction reaction as well. And so what you're looking at here is that blue bar in that container. And that container can either be, an alkaline bath with zinc in there, or an acidic bath with zinc chloride. And that means that you have the ions in there to give you that electrolyte. So as you use a power source, again, the oxidation is going to occur at the zinc, that blue bar, and the electrons are going to flow, and the zinc is actually done to plate out on that ferrous gray bar there. And so that's how they do it, with electricity and the certain type of bath. And as I mentioned before, there again, you're doing it to improve corrosion resistance, but really increase the service life and improve the functionality. So many times you might see that you're increasing the wear resistance or lubricity, and those are the things that are more important to you, or just as important as corrosion protection. And a lot of times you do it because in manufacturing, it's a lower cost method of producing a part, because you want to be a low cost producer if you're producing something so that people want to buy it. So thin coatings of relatively expensive metals on a cheap substrate is a popular, is really popular, I guess, from a standpoint of manufacturing. So corrosion preventatives can come in a number of different forms. Probably, as I mentioned here with WD-40, that's a kind of a solvent, water displacing type of corrosion protection preventative. There's also different types of oils, and they do put some of the VCIs, some of those amines in the oils as well. Sometimes they fog those in, like in an engine, and I'll show you what that looks like a little later here. But again, it could be greases, and the image there, what we're trying to show is that we'll produce or manufacture, a vehicle, and because it may be in storage or we're shipping it overseas, we'll have to put on some sort of what we call in-transit removable type of rust preventatives. And so we'll put some films on there so that you can wash them off. It could be an oil, it could be, like I said, it could be water-based, it could be a number of different things, but it helps protect and slow down the oxidation when it gets to the point of use. Now over on the right, these are methods of things that I mentioned before. There you're seeing some paper that's been treated with the amines, and it's a VCI type of paper. So again, if you buy something from an automotive store, you will see in many cases that they're going to be wrapped in some sort of paper, and chances are, because they want to maintain it on a shelf, you can actually package parts and leave them on a shelf, even in a relatively maybe not an air-conditioned environment. You can store things, if you know properly, with VCI paper and film, for 5 to 10 years. And some of the auto parts stores, they really look for that, because the last thing you want to do is get the customer opening up something and then, he's got some corrosion. And then over on the right-hand side, we're just showing that same type of VCI type of impregnated film, but this is kind of in a shrink film. So it's a way to actually, using heat, they can shrink wrap that part. Below that, you see that white tape from Rustex there, and tape by itself can prevent moisture and oxygen, but this tape actually has some VCI in it, so it provides further protection. And then down below, these are emitters. And so a lot of times people will take like some of their toolbox, and they will, because there's not air moving across it, they'll put in some of these emitters to help preserve some of the different types of tools they have from further oxidation. Not to spend a whole lot of time on this, but anodizing is an electrolytic passivation process used to increase the thickness of the natural oxide layer on the surface of metal, and then for primarily you see it on aluminum. And what's nice with the with these I guess carabines, these clips, it's a very, very thin coating, and they can dye it. So when you start seeing some aluminum, you might see some really pretty colors. You'll probably see it on some of the water bottles as well that are aluminum. And over on the right, there's a picture there. I'm not sure that picture actually shows the anodization, because there's other types of coatings that they put on there, but it is common on cookware for certain types of areas, especially if it's the right metal here, aluminum, or some of the other metals that they want to anodize. They can put a very, very thin coating on, and to make it pleasantly aesthetic, have that appearance that you're looking for. So moving on here, I mentioned material scientists. These are, I work with some of the individuals in material science, and one of the things that they get involved in is really investigating how materials perform and why they fail. And so over on the left-hand side, you can see that there's that windmill shaft, and I believe that they were probably seeing some cracking on that windmill. So obviously they wanted to see, stress, or, what was the reason why there was some fatigue. And what they use are instruments such as a scanning electron microscope to kind of see, below the metal surface of what was actually happening to the grains in the actual metal. And I think on the right-hand side, this picture here is kind of showing that there was an overheated location on the shaft, which was the root of the cause of the failure. So just to give you an idea of one of the things that some of the material scientists do from the standpoint when they're doing, looking at failure analysis, this is what they get involved in. Obviously chemists do a number of different things, and the slide that we have here to kind of show is really they use certain instruments, a number of different instruments. But a lot of times, especially in my early career here at Caterpillar, I worked in the lab, and people would come to me in the manufacturing environment, and they say, hey, I got something in my fluid, what is it? And so you would actually test the actual fluid without that material in it, and you would use, maybe an IR, spectroscopy, or, different types of things that you'll look at, both the known and the unknown, to try to understand what's actually occurring. And so it looks like somebody came to our organization and had some gelatin, kind of a gelatin type of buildup on this hydraulic filter. And eventually it was identified that this diesel exhaust fluid, was used in was used to reduce, which is used to reduce the amount of air pollution and stuff. But anyway, that DEF somehow got into the hydraulic system. And so, it formed a gel. And so it's just an idea of other things that what chemists do in the manufacturing environment. They'll get involved in situations like this. We might develop a certain type of test and follow it to try to recreate corrosion, accelerate things. But I wanted to give you an idea of some of the people that we work in when it comes to corrosion, what they get involved in, as well as some other issues such as this. And then manufacturing engineers, they're really focusing on improving the production. And so a lot of times chemical engineers will have a similar type of function, but really what you're trying to focus is to turn really raw material into kind of a new product and doing it in the most effective, efficient, or economic way. And so I just took some images here, or I should say Anka took some images here, from the standpoint of looking at a robotic line on, I think on the right-hand side, it looks like an automobile plant. Pretty fascinating. I've been through several of them over the years. And then it looks like we're dealing with some smaller parts here on the left. But, and then over the years of my experience, I've worked in a number of different things. I started my career in water treatment, and then I got involved in painting and painting processes, but all those really involved cleaning and machining protection up on the far left-hand side here. And so, as I mentioned early on, metalworking fluids and some of these wash tanks or cleaners, and we went and remove and clean the parts so that it's good quality water. And then essentially after the parts are dry, those parts get packaged. And Anka and I had the responsibility for the specifications for packaging and for the specifications for plating. And then moving over this engine preservation, and depending on where the engine's going to go, in most cases you're going to remove some of the oil. And so I mentioned volatile corrosion inhibitors that are in that film. We can also take those volatile corrosion inhibitors and you can fog it in. And as long as you're containing those, that type of the fog, and make sure that it's not going to escape, that'll again go through the system depending on if it's easy pathway and microscopically protect those surfaces. Over on the right-hand side, I mentioned this a little earlier. This is a little quite interesting from the standpoint that you think of stainless steel and you don't think of it's going to corrode, but there's different types of stainless steel and different alloys. And this one here was 304, and 304 cannot handle high chloride concentration. So you make a very corrosive environment, and you see the decrement of the erosion that you see on sidewalks and creating potholes. But high chlorides, and it doesn't take much, 400, 500 ppm, and water that's being recirculated in the system, it started this type of corrosion that was occurring. And then, because once you start, it's like the human body, there's just not one thing that's occurring. Then generally, when corrosion starts, especially in something that's seeing kind of high volume of water, it could be due to additional types of things could be occurring, such as, high bacteria, sulfur-reducing bacteria to kind of increase those rates and cause other things that occur. Then on the bottom left, you'll see that these are some of the things that we run in a kind of an accelerated corrosion test chamber. I'm going to show you some of the tools that people use in the industry. And then you're looking at some pump shafts, and here we're showing the difference if you put a plating on. In this case, it was electros nickel. So the two on the right-hand side were plated with electros nickel. The one had no plating. And if you put that into kind of an accelerated environment, in this case, we use a salt spray chamber. You can see the big difference, the advantage that the plated part has with something that has no protection. So those are just some of the tools that I'm going to show you. And then again, we get involved, like I said, in promoting good practices and specifications on, in-transit types of corrosion prevention, throughout the whole supply chain and on our finished product. So I have just a few slides here left, but I just wanted to kind of show that these are some of certain instruments that we use. The The salt spray chamber is typically used for, corrosion preventatives. It gives you kind of a accelerated environment, especially near the sea, or if you're sending something overseas, kind of simulates more of that environment with higher chlorides. In the painting world or automotive industry and Caterpillar for our machines, when we talk about painted components, we use the chamber of cyclic corrosion chamber. Very similar in many ways to a salt spray chamber, but it has different cycles on it. So it's not seeing that salt all the time. And then over on the right-hand side, there's no salt. We're talking about humidity cabinets, and that's typically used for part packaging. And to show you, as I mentioned, as we receive parts, and do we have the right package to make sure that we prevent condensation, or we prevent the formation of any corrosion. And Anka and I are big fans of the real world corrosion. So if we ran a test, it'd be great if we ran and got the same numbers with accelerated corrosion, and we typically see that. But we created a rack, and we put certain panels with RPs, rust preventatives, or corrosion preventatives outside in at our facility to kind of see which ones actually do a better job and which ones can be cleaned off easier. One of the better long-term projects that we ran is we made 4 test kits working with a company called ChemTool. And we sent these 4 test kits, which considered of chrome rods as well as panels throughout the world, 8 different locations throughout the world. And we took pictures of them, or had people take pictures of them to kind of see the formation of corrosion and how well the corrosion preventatives work. And then dealing with water, we've done a number of different things with linear polarization. So you can see kind of how the fluids, if you're trying to recycle water and what you're going to do with that water, how's it gonna stand up to the different types of environments that it's going to see in the piping system. One of the tools that we use, and is pretty inexpensive, is this temperature humidity sensor. And so we will, when we package parts after we've cleaned them and package them, or our vendors are sending us parts to prove out a process and to validate it, to make sure that it went well. It's nice to know what environment it saw. And so you can set these things, they roughly run $100. You can set them up so that they actually will give a reading out, every 10 minutes, every hour, every day. And so we typically like to put them inside the package and then outside the package to kind of track the environment that they see. And here's just to kind of show that what the graphs that you'll see. Over on the right, we came across this website. I'm guessing that it's still available, but I didn't really explain this before, but when you start seeing a relative humidity of 50%, then this is why you look at different parts of at least in the United States, why you see certain corrosion in certain areas, and places like Arizona, you don't see as much corrosion is because of humidity. And so you go to this website here and you can plug in the temperature, humidity, it'll give you the dew point, but it'll give you the idea of what the risk is. But I will tell you that you start getting above 50, 55%, and your risk is gonna be higher, from a standpoint of that you have a corrosive environment. So might be something of interest. So 2 slides here. I'm gonna reinforce this slide here of galvanic corrosion. So you're seeing this rusted steel chain. And, in this case here, this was close to the sea coast, like I said, so it's more corrosive environment than in Peoria. But you'll see that the similar metals, you're not seeing the corrosion on it. And the anode is essentially the rusted steel chain. And so you can use this to your advantage. So here you're showing a bunch of dissimilar metals, and this is, zinc or galvanized here. But, electron flow, oxidation is occurring at the anode, and that's where the chain is. And so flow of electrons, are causing the corrosion. So we got about 5 minutes left, and I want to talk about a couple things here, or this last thing, how you can do things if you're a homeowner to save money. A lot of people don't know this, but water heaters, typically cost maybe with purchased and installation anywhere from, $500 maybe to $1,800. sometimes can be more expensive if you have a larger water heater. And but inside the water heater, you know, as we mentioned, you got that environment of, you know, exposure to water. What they do is they create this sacrificial anode. As we mentioned, you know, corrosion occurs at the anode. And so they put in, this is where you can use galvanic, a technique to protect the thing that you want. So by making the anode and replacing the anode, you can extend the life of your water heater. And obviously you want to use a professional, or you want to make sure that you understand all the risk involved. You know, if you replace this sacrificial anode rod, but each of the water heaters, most of them will have, you know, the ability to remove it. Sometimes it's a little harder on others, but it's going to be roughly, I think it's standardized, maybe it's a 1 in 1/16 deep socket hex. But most of the times you're going to remove a large rod. But if you do this periodically, and depending on your water, you can really extend the life and save a lot of money, because you won't have to replace this water heater. And I prefer, because of the headroom that I might have in the different, or in the houses that I've owned, these flexible sacrificial anodes that you can buy. These are a little more expensive, but again, you can replace them with very easily. You might have to cut the other one out because you don't have enough room to pull it out, but you want to replace it if you have a headroom space of this. So it's just a way for you to be smarter than your parents, or, you know, explain to them that you have an opportunity to maybe save them some money on down the road, but you can really extend the life of those water heaters. So I know we have a few minutes left. I can turn it back to Nick here, and Anka and I can address some questions.